So for people online can hear as well. So, hello? Okay, yeah, I can hear me from my own screen. So welcome to another Oryna seminar. It's the first seminar of this new year and also this new semester. And actually the semester, I think will officially start in this week, probably not today, but happy to see everyone again. And we'll probably do a round of introduction, probably on the Wednesday or the next week's one, because the next week we will have more people to show up. And today we have our speaker.
So today we have Oryna Ivashtenko. Okay. She's a 4-year PhD student at Weizmann Institute of Science in Israel. So working with Barak Sakeh.
Okay.
Previously, he also did his her master also at Weizmann and a bachelor from Ukraine. So thank you. Please come in.
Thank you very much for this introduction. I'm very happy to be here, and it is an honor for me to have an opportunity to present here. So I will tell you today about how we want once again to use Kepler data, because many people already did it, but we want to do it again, to detect small long period planets a little bit better than we used to do before, and then how we can use it for inferring something about science. Before I actually talk about science, let me introduce my group. We're not an exoplanet group. We're not focused on exoplanets. We are a group working on statistics, algorithms, and detection methods in many different fields of astrophysics. This is Barak Zakkai, my advisor. His background is in mathematics, and in physics, his background is from gravitational waves. And in gravitational waves, it's very important to have very precise detection methods, because the signal is very, very faint. And you need to know how to implement optimal statistics. And then it turns out that many of the methods are exportable to other fields, because it's basically time series analysis. So for example, I'm working on exoplanet transits. Ariel working the same approach, but for the gamma ray burst detections, for pulsar detections. This is still the gravitational wave group. And exoplanet-wise, we both do transits, radial velocity, and high contrast imaging. So we're very diverse. We're not focused on specific physics. We're focused on developing statistics in different fields. And specifically, my project is about using those precision methods for time series, but in application to exoplanetary transits in Kepler. So what is the main goal? This is probably the most recent occurrence rates table from Kepler. Kepler is the best known mission for occurrence rates, because it has a good selection function and consistent observations of the same field. So the easiest to do populations and the most precise is from Kepler. And also Kepler is the most photometrically precise. So we can go to the smallest possible radii and to longest possible orbital periods. And in principle, people did a very good job on measuring the occurrence rate, except for here, for long periods more than 50 days, and for small planetary radii less than 2 Earth radii, in which, first of all, we don't have enough points, just enough detections to have some reliable estimates here. Why we don't have enough detections? Of course, we have detection biases, because this is long period, so we only can have like 5-ish transits and sometimes 3. So we don't have enough transits in our data, and Kepler data is 3.5 years roughly. So this is our limit. These planets are small, so it's low signal to noise, and the probability to transit is low, because in order to transit, you need to cross the line of sight between the observer and the star. And the further away is the planet, the smallest is the probability to actually be there. And therefore, for those planets with long periods, even if they are abundant, their probability to transit is about 1%. So we don't have many of them available for detections. But in addition to that, we have another complication, which is in our data processing. And this is the problem with the reliability. Why reliability is important here? Let's understand how do we go from light curves to the population estimate. So we have light curves, they go to the detection pipeline, which basically detects if there is some periodic planetary signal in the data. Then from a detection pipeline, you collect events. They go to the vetting pipeline. You check that it is, for example, not an eclipsing binary or not a background source or something like that. From them, you form a catalog, which is basically your objects of interest or your planetary candidates. And these planets, they go to the population inference and you count how many of them you got in which part of parameter space, etc. But of course, it's not enough to just have your catalog. First of all, you need to understand how many planets available you detected, which is a completeness. So you cannot do population inference without completeness. For example, there were 100 planets, but only one transited. So the fact that you detect only one doesn't mean that there is only one. Also, there's a completeness of your detection pipeline. Maybe your sensitivity is such that out of one, you only detect 1 in 100 or something like that. So it's very important to understand. And another thing, which is even trickier, is the reliability. Say you have a planetary catalog and you think, oh, I count 100, but maybe out of those 150 are false alarms or false positives. And then you will just get wrong population inference because your catalog is contaminated. So it is very crucial to take into account this completeness and reliability. With completeness, Kepler did a very good job. They characterized their completeness well, and their completeness is actually good enough. But with the reliability, it was kind of tricky for these long periods and small radii. And in 2020, Stephen Bryson, one of the members of the Kepler team, wrote a paper in which he estimated the impact of the reliability. And he said that if you don't take it into account properly, you can have a factor of 2 error in the occurrence rate, in addition to all the other errors that we have. Yes, and the reliability of the Kepler pipeline has this.
Can I ask a
Yes,
question? I know
sure.
it's just a flow chart, but it seemed like you had 2 different ways of getting to the population inference to like bypassing the vetting pipeline or not.
Oh, no, this is just it shows that for population inference, you need both this and this. So you need to take into account all of them.
I mean, is that saying there's sort of 2 different completeness and reliability?
Yes, yes. You can miss something on the detection stage. For example, you just don't have enough signal to noise for your pipeline to detect it. And then if you already detected it, your vetting pipeline can, for example, say, oh, I think it's an eclipsing banner. So you see that there's something with a high signal to noise, but you might confuse it with an eclipsing banner or with something else. So for Kepler, this completeness and reliability are the completeness and reliability of Kepler RoboVetter. It is their automatic code to characterize whether it is a contaminant or a planet. But before that, you need to know the completeness and reliability of the detection pipeline itself. And I think that one of the important problems was specifically here, because the pipeline can produce events which are seemingly high signal to noise, and it will be hard. Well, they are high enough to detect, but they are low so that there is not enough information to characterize it well. You see a dip, but you don't see its shape, you don't see the centroid motion, you don't see the background motion. So you don't have enough information to tell anything else apart from the fact that it is a dip. And the dip, it turns out, can be spuriously produced by some other effects in the data which are not planets. I will just explain it in the next couple of slides. Yeah, so this is the reliability of the Kepler catalog. And what is reliability? It is the probability that a given event in your catalog is actually a planet and not some false detection. And this MES is multiple event statistic, is a detection statistic combining all the transits in a given star light curve. So if MES, MES is like signal to noise. You can think about it as signal to noise. And why good measure is 10, like why we need signal to noise 10 to tell something about this detection. It is because the Look-Welser effect. When you look at a lot of data, and Kepler is like more than 200,000 light curves, and they're long, and there are a lot of different periods. when you do many, many trials, testing many different options, many different stars, many different periods, just out of nowhere, out of random Gaussian noise, once in a while you will have a seemingly significant detection. So when your searches are very large, you have to make the statistical correction to properly understand what is the false alarm rate that you will naturally get just because your search is very large, and then to put accordingly the detection threshold, and then sometimes you will need some 5 sigma, 10 sigma or something to be able to even claim a detection. Here 10 is an overkill, like usually you need 7.1, which was a calculated value for Kepler, but they just show it what if SNR is above 10 or below 10. So for above 10, the reliability is basically 1. Whatever gets into the catalog is a good planet. But when it gets smaller than 10, basically it drops as function of period. And for our like long periods, more than 100 days, it gets less than a half. So when you get your catalog, probably more than a half of your catalog are false alarms and not real planets. And then, of course, it is very hard to do population analysis out of this. And a good way to see how it happens is the following. So how we actually understand that our reliability is bad? How do we know what is the false alarm rate? How do we know what is the planet's rate? Doing it from simulations, just simulating lead curves and trying to run the pipeline is a bad idea because you simulate only the noise that you think it is. But all the issue is in the fact that you don't understand what the noise actually is. And the real data is more tricky than a normal Gaussian noise or something simple. So what people do, they take the actual light curve, they scramble it, they take pieces of data and they permute them in such a way that all the periodic transits that were there get destroyed because the periodicity is destroyed. But all the noise properties, all the glitches, all the pixel sensitivity drops, cosmic rays, and everything are preserved. And then you run the pipeline exactly in the same way as you would run normally, but on the scrambled data. And then you guarantee that whatever you discover is not a real planet, it's something else. And here, Kepler took their normal search, all of those blue points, and they compared it to the scrambled search. All of those colored points are searched on mock data produced from the real data. This is log number of transits, which is like inverse periods. So this is long periods, this is short periods. And this is, again, this multiple event statistic in units of signal to noise. And you see that their nominal detection threshold was 7. So at 7, you seemingly can claim a detection. But you can see that here at 7 and 8, and even at 9, we have all of those colored points. And there is the same number of colored points as blue points, which means that the mock search discovers the same number of events as the true search. So it means that half of the events in your catalog probably are false in the same way as you got them in the false search. And even if completeness was good, so probably most of the planets that exist in the data actually made their way into the catalog, but together with them, we have all of those false detections, which we don't want to be there, and it is hard to tell apart like which one are which. And because of that, estimating the occurrence rates got even harder and people got basically stuck there. Question, yes?
Do you keep the transits in the scrambled light curve?
So there are different ways to do it. Obviously, like if you have something like huge, it's better to remove it. But many times when you have a small transit and you combine it with something which is like 0, it doesn't produce a very significant event. So like when I do this, I do it in 2 ways, with keeping the transits and with not keeping the transits. Why sometimes I do keep the transits? Because I don't know whether they are transits or not. If it is a false alarm, then if I remove it, I'm biased towards lower noise. So it's also like scary to remove it. It's also scary to keep it. So I'm not sure what exactly they do. What I do is I have 2 searches, both with removing and not removing, and then I have a statistical sum of both in order to estimate the expected background if I don't know what exactly is the source of this detection. And just to illustrate who are those weird false alarms, in the 2018 Kepler paper, they have this riddle. So these are basically single transits that were folded to produce this. And from this, one is real and one like real as of found in a real search. And the other one is found in an inverted search, in which by definition, you don't have transits because everything is upside down. And they ask us to guess which one is from the true search and which one is from inverted. They look basically the same. And this is just to illustrate that data is tricky and it is full of those false alarms, which you cannot tell apart from the actual transits. So our goal is to somehow try to fight those and write a statistical method to be able to enhance the significance of real periodic planets and downgrade the significance of the false alarms.
Bottom one, the real one.
I think that actually the top one is the real one, but I already forgot, like, you know. Yeah, so in order to change something here, we basically had to like do something different in all of the stages in this scheme. And today I will mostly talk about this because this is like the main change that we did, because the main problem that we want to solve is exactly because here Kepler detected some false alarms which should not have been detected. So we want to kind of renovate this in order to solve this problem. And we just wrote it from scratch from like an empty Python file, a new detection pipeline. Yes, so we write a new detection pipeline with the goal of a better search reliability. And I'm now going to go through the main methods of the pipeline. So we start from the very basics, writing a detection module. What is our noise? What is our signal? And what we want to detect. We are looking for something like that for transit in the data. We start from looking for one transit, and later we will combine several different transits into a periodic planet. We model our data as Gaussian correlated noise with the covariance matrix, and then it maybe contains a planetary transit, which is described by template, this red thingy over there, multiplied by some amplitude, which depends on the planetary radius. And this is a classical detection problem of a signal in a Gaussian noise, for which there is an optimal detection test, optimal in the way that for a fixed false alarm rate, you have as big true positive, like your completeness is the best for a fixed false alarm rate. And then when you solve, and for this test, the optimal detection statistic is log likelihood ratio. And when you solve the algebra here, you get the following detection statistic of how to detect such a signal in such a noise, which consists of basically the data, the inverse covariance matrix of the noise, and the planetary template. So you match the template to the data, weighting down by the inverse covariance matrix. Why it works in this way? It is the easiest to understand if you go to the Fourier domain. Just it is like an inner product between three components. You go to the Fourier domain, it is exactly the same, but in a different basis. You have your template, your data, but instead of the covariance matrix, you now have something which is called power spectral density, which is basically what is the power of noise for every frequency. And this formula tells us why we need to have this weight of the inverse covariance matrix. It is because different frequencies have different amount of noise in them, and then we have to account for it using weight. So if a given frequency has a lot of noise, we divide it by a large PSD, so we downweight noisy frequencies and we upweight frequencies with a little noise, so we optimally summarize all the information which is contained in all the frequencies of the data. And this is like an intuitive way of how to understand why this detection statistic is the best. And of course, writing nice formulae is good, but in reality, we don't know age because we don't know which planet we're looking for, and we don't know PSD because it depends on the star. It's going to be different for every star. It depends on time. It's going to be different for every Kepler observation period. So formula is great, but we don't know the components. And then for the template, we use the template bank, meaning that we generated many shapes of planetary transit. We made sure that whatever planet we want to detect, there's going to be a template which will match it closely enough. And then we use this we run this on all of the data, we run all of the possible shapes, and then we basically calculate this statistic for all of the possible age that we can have. Many times people use boxes instead of planetary, instead of transit-shaped templates. For deep transits, for large signal-to-noise, this is okay. You will basically get most of the information that you need. But if your signal-to-noise is small, it is better to match exactly the shape, because otherwise you risk to lose signal-to-noise, which you cannot basically afford. Yes.
Is there significance to the colors?
Yes, colors have the weights of the template prior. We also calculate what is the probability given physical limitations, for example, a given distribution of eccentricity, inclination, and things like that. How many detections should every template on average have? For example, some of them are expected to be very rare, and some of them are expected to be very frequent, and we want to attach to them proper statistical weights in order to upweigh something which is more likely to be a planet.
Can you say a little bit more about what goes into the template bank? It sounded like obviously some orientation,
Yes.
different marketing models.
Yeah, so there are many parameters of the system, about 6. So we have the orbit, which has its eccentricity with a pedestrian angle, inclination, of course, semi-major axis, and the star itself, it has some limb darkening model. So in principle, all of them should go to the definition of the transit shape, but it turns out that the transit shape is very degenerate. For example, you can get the same shape if you just make period shorter, so it's going to be faster and the shape shrinks, or you can get the same shape if you have eccentricity and you're oriented in such a way that the transit is faster and the shape shrinks. So it turns out that you don't have to sample properly this 6-dimensional parameter space and have tens of thousands of templates. It is enough to have around 60 of them, as I showed you before. And we built this bank by this method, which is called random sampling method. So basically, we take all of those 6 parameters, we sample them according to the geometric probabilities that the orbit is oriented randomly, the eccentricities can have uniform distribution, you can have uniform angles, etc. We generate all of those different angles and parameters, and then for each one of them, we check whether there is a template in the template bank which matches it closely enough. What does it mean, matches closely enough? We calculate that optimal detection statistic, which is basically the signal to noise that we get. And if signal to noise is like 97% or something like that, then it's okay. If it is too low, then we add this model that we generated into the bank. So the bank by itself accepts all the models which it cannot detect, and it builds itself in such a way that it can detect everything. So here, those small triangles are the templates which actually made their way into the bank. And you see that for like all of this blue space of all the parameters that we generated, it is enough to only have those triangles in order to detect them closely enough. Limb darkening, we tried like several different models just to make sure that it's okay, like we still detect them. And another important thing is actually the power spectral density, because it enters the detection statistics. So if a template bank is built for one star, there is no guarantee that it will work for all the stars. But we generated them with an averaged PSD, and we made sure that it's also fine for most of the other stars with the variation in the PSD that they have. So basically, it requires us to make the template bank a little bit more detailed, add a little bit more templates so that they don't get far away from each other when the power spectrum of the noise changes. Does it answer your question?
Yeah, I guess I'm wondering about the cross correlations between these parameters.
Yeah, well, I mean, as I said, everything is very degenerate.
Right.
Yeah, it is just how they would be physically distributed, and it's selected based on the templates. Also, the templates are correlated. So when one template gets a statistically significant detection, many other templates would also do it. We have a way to summarize it. I will show you later. But yeah, everything is correlated between each other. There is a different way to build a template bank, which is to orthogonalize the templates. In principle, people do it, but here the bank was so small that we're like, okay, let it just like be what it is and not go too complicated. If you are interested to see how we measure the power spectrum, I can talk about it, but it was not my plan because it is a little bit too technical. So let's jump straight here. Yes, I want to continue sharing. So we calculated this, the detection statistic for a single event. And now we want to transition to the multiple event statistic because eventually we want to look for multiple transits for something which is periodic. In principle, people also look for single transits, but for us, a planet is a good planet only if it has more than 3 transits. So if you just write the detection problem for multiple transits and then do some algebra, you get that the multiple event statistic MES, which is this, can be obtained from the single event statistic SES using this summation. So you basically sum all the single event statistics and you normalize them by the variance. They all should be Gaussian random variables because we wrote that model for Gaussian random noise, and then we just calculate a convolution with something which should preserve the Gaussianity of the noise, and it should be just sum over Gaussian variables normalized by variances. It should be a nice Gaussian variable, which is a good background for detection. This is what it should be, and it should work, but the actual problem of this entire project is that in reality it doesn't work. This is this single event statistic squared. This is the count density in the log scale, and this is Gaussian. So it looks like a straight line because this is squared and this is log. So in a good case, the background should be parallel to this line, but in the real case, it has this fat tail, which means that the noise is not Gaussian, and all of these events in the tail actually produce this contamination that we saw in the beginning. Why it is so bad? Because then we will look for periodicity, and the good case is when we will have 2 transits combined into something significant. Single transits here are not significant. Many times when we look by eye, you remember we saw those single transits example from Kepler. When you look by eye, many times you don't see a transit at all. So the only significant thing is when you combine many of them and they sum up into something significant. But when we have this, we can have the situation in which something which is basically 0 combines with this big event from the table, from the tail, and it will produce something with the same significance as this, and we will not be able to understand which one is which one is good and which one is bad, and it will basically produce all of the contamination that we saw. So on this, we cannot hope to detect small transits. They will basically get completely buried in the noise tail. So what we do to this tail, first, if we are able to vet them at this stage, for example, if something really big here happens to have non-transit-like shape, we can just reject it from the beginning and not even let it to participate in the periodicity search. Sometimes it is possible. For example, here, those blue points, it is possible to write a test saying that it is non-transit-like, it's probably a glitch, just remove it. How do we do it? In principle, you can write a chi-square test, which will just say, okay, the residuals are too large, but chi-square tests have their number of degrees of freedom. And the bigger is the number of degrees of freedom, the fatter is the tail and the harder is to tell apart a significant chi-square from a non-significant chi-square. And if the transit is very long, we will have many points which will give many degrees of freedom, which will make our chi-square test weak. And we don't want this because weak tests cannot detect things for us. We want a strong test, which means that we want a small number of degrees of freedom. So one of the possible approaches is to have, for example, 2 degrees of freedom, cut the template into 2 parts and say, this is one detection statistic, this is the other detection statistic, and we will measure the amplitudes of the two parts. If the amplitudes are the same, it means that it is consistent with the transit shape, it is good. If the amplitudes are too different, it means that it is not symmetric, not transit-like, not as we expect the transit to be, so we can reject it. And the same we can do with 3 parts or with 4 parts. And that basically gives us a chi-square test with 2 or 3 degrees of freedom, which is more powerful, and we can reject many of those bad-looking events, which brings us from this tail to a little bit smaller tail. It is good, but it is still a tail, and unfortunately, we could not reach a Gaussian distribution with this. So we had to go hard way and say, okay, let's admit that the distribution is just non-Gaussian, and we could not, in the very beginning, write this Gaussian model as we did. So we went to the very, very beginning and rewrote the model in order for it to be non-Gaussian. And it turns out that mathematically, it is exactly the same as before, but we should add this so-called non-Gaussianity correction. It basically measures the distribution, the likelihood of getting this single event statistic given the non-Gaussian noise as opposed to given the Gaussian noise. So for every statistic, it says, what is the probability that it was generated from this non-Gaussian tail as opposed to a normal Gaussian tail? Of course, this distribution is not known because it's not known. So we measure it from the tail that we actually obtain. This is just the Gaussian. This is what we measure. And then we substitute this and this here in order to calculate this non-Gaussianity correction for every event and like subtract it to get a statistic which will be well behaved. And after we subtract this correction, we get this green thingy, which basically follows the Gaussian distribution. This is good. This improves our reliability. An important thing to say that it not only punishes the noise events, it also punishes the planetary events because it is only aware of this value of the detection statistic. So everything which has a large detection statistic gets a non-Gaussianity correction. So we will lose planetary signal to noise. You will see it in what follows. But the important thing about planets is that they are truly periodic, and the contamination signals are not expected to be periodic. So even if we lose signal to noise for every transit, when they accumulate all together, they will still pile up into something significant and still have a way to distinguish between planets and non-planets. So even if we lose signal to noise, we can still have hope to proceed and to detect something. Okay, so where we are, we got this with all of those methods. Then we combine them into the multiple event statistic. We have all here another like veto of comparing the depth of different transits of the same planet. We want to make sure that they're the same. And after we do this, we need to find the best trigger. But again, the best trigger, we don't want it to be just the biggest detection statistic because, as we discussed before, we have priors. Some events are more likely, some events are less likely just from the physical point of view. So for some regions of parameter space, signal to noise 10 means that maybe it is really a planet because planets are very common here. So the likelihood to have a planet here is large. For other parts of parameter space, planets are basically non-existent. Like it is just forbidden from some physical considerations. And even if you detect something statistically significant, probably it is not a planet because it's just so physically unlikely. So this is why we want to have prior, which will add as a weight to all of our likelihoods, to all of our detection statistics that we measure. And then we integrate it over all the parameters that will make the search. So we make the search over all the periods. We make the search over all the time shifts inside the period and over different template parameters, which basically summarize for us the real physical parameters like eccentricity, inclination, and so on. And this full likelihood, which is this integral, is basically answering the question, what is the probability that for this star there is a planet, any kind of planet, for any period, any time, some planet existing around this star? And from this likelihood, in the same way as we get detection statistic from this point likelihood, we can also write a detection statistic, which we call IMES, integral multiple event statistic. And this is the final product that our detection pipeline calculates, and this is basically what we report as our detection statistic for whether there is a planet or not. Any questions at this stage? Yes.
Yes, I'm a little worried about the prior, in the sense that if you're trying to remove previous erroneous data, but that data is informing your prior.
Yeah, so this prior is mostly geometric. It's just the orbit is has a random pointing in space, or like the prior that the eccentricities are uniform or something like that. There is a prior of occurrence rates per periods and radii. It is also inside it, but for up until now, it's basically a normalization factor. It's not like very important. There is the period part which enters there, but it's like a shallow prior, so that it doesn't give as much difference as it could otherwise.
That's just a geometric prior.
Mostly.
Okay.
Mostly geometric. There is going to be now a part of non-geometric prior, but I will explain to you how it can be like accounted for. Yeah, so your concern is very real. So we are now here. We got this detection statistic, and now still we want to understand on a larger scale what is the probability given this detection statistic. What is the probability that we come from the background noise or from a planetary population? So we want to have this statistical significance evaluation for every detection. And as I said, there is a scrambled search, which we also implement. But as opposed to Kepler, we do scrambled search per star, because stars can have different background, different non-Gaussian distribution and everything. So we make scrambled searches per star, and this gives us what is the background noise for every star. Also, we do injection recovery to understand what is the completeness for every star. So we take the planetary population, inject it into the star, and see which planets our pipeline would be able to detect. And then we combine them to calculate what we call p-planet score, which is a measure of the probability that a given signal is a planet and not a noise event. This is how this p-planet score is calculated. Basically, this is the distribution of planetary events from injections. This is the prior, and this prior is not only geometric, so it is important. And this is the same plus the opposite term, in which we measure everything, which is 1 minus planetary prior, the probability that it is not a planet, times the distribution that we got from the scrambled search, the distribution of the noise. And this is how it looks like graphically. So this is the detection statistic in units of SNR squared. This line is the SNR that we got from our event. Like, let's say around this star, there was something which is suspiciously looking as a planet. So we run this scrambling search and obtain this distribution of the background, this injection search and obtain the distribution of planets. And here we compare them and we divide them and we calculate this p-planet score. Now, how does the prior get in here? Basically, its biggest contribution is that it just multiplies this injection histogram. If the planets for this period are twice as common, this is going to be just twice as high, which means that our p-planet score will be twice as large as it is now. And in principle, since we have very large uncertainties on the population now, this is also highly uncertain. However, after we have many candidates and after we use them all together to infer the population, we can self-consistently correct for it. So given our new update with all of the candidates that we can now summarize, we adjust their prior here so that they're self-consistent with the number of events that we detect. So because it is just a multiplicative factor, we don't have to run those thousands of simulations again. We can just correct it post factum to make it self-consistent. Yeah, and just to illustrate, this is something like 90-something% p-planet, so 90% that it is a real planet, and it will look something like that in the folded state. So you basically cannot even see by eye that it is a planet, but the detection statistic tells that it probably is. And this is the signal, like the detection statistic time series, basically. This illustrates why it is good to run a detection statistic as opposed to just look at the data or something, because it is optimal, it enhances the signal where there is a signal, and it shows nothing when there is no signal, just, an example of how it works. Yeah, and now we basically built the pipeline, we understood how it works and why it works, and let's make sure that it actually can detect something in the real data. So we took Kepler confirmed planets, we ran the pipeline on them, and we calculated, this is log 10 of 1 minus p planet. A little bit confusing, but what it says that if this number is very small, it means that 100% for sure it's planet. So it is not planet with probability of 10 to the minus 10. For sure it's planet. And if it is close to 0, then we don't really detect it. So out of 134, we have 1, 2, 3, 4, like 5, 6 that we cannot really detect. And all of these, it is like more than 99% detected. So it says that we are okay, we're detecting something, we can proceed and try to run the pipeline on something else.
Where did
Yeah.
the 130? What is that sample? Where did those come from?
Kepler confirmed planets, NASA exoplanet archive, filter everything by confirmed, and detection statistic small, because large detection statistic, we don't care. We think Kepler is complete and reliable there. We don't want to search for them. We searched only for detection statistics smaller than 12, I think, or something like that. Yeah, and then you see that the planets which are not detected, they are all like long periods. So probably we are incomplete for long periods. Why we're incomplete for long periods? Because this non-Gaussian correction, it gets larger when the transit gets deeper. And for long period, to collect the same overall detection statistic, you have every transit to get deeper because you have small number of transits to summarize. So here we have to have deeper transits, and we have to apply to them a larger non-Gaussian correction, and then we lose them. And intuitively, it can be understood as if your data is non-Gaussian and you're contaminated by something which appears randomly and looks indistinguishable from a transit, and you have 3 points like that, how can you know whether it is a true periodicity of 3 points or it is just 3 events which conspired to follow one another? It's like, if we don't have any other way to test whether it is planet or something else, just from this information, it's really hard to distinguish 3 randomly aligned things from 3 events of the true periodic transit. So when we measure our completeness by taking all the light curves and injecting planets of given period and given signal to noise, we can compare it with Kepler, and we get that indeed for long periods, our completeness, this is fraction of planets detected, and this is the detection statistic in SNR squared. Sorry for that, because for Kepler, they use units of SNR. So like their 8 is our 64, something like that. So basically, we lose here all of the planets which are like more than 350 days. Like most of them we lose, but still here, like Kepler, like 6 to 8, 6 to 10, something like that. So for us, it is like here. We do have periods for which the detection completeness is actually high enough. And even here, if it is like around 50%, we still can detect half of them and still use them for the population analysis. So the conclusion from here is that our completeness is on average worse than Kepler. And this is the price that we had to pay for the reliability, which I will show to you next. When we ran our search over the entire Kepler data, we got this distribution of detection statistic in units of signal noise squared. And when we scrambled all of the Kepler data, we got this orange thing. Now we can compare it to the Kepler that we saw before. So you see that for 8 and for 9, we're still highly contaminated. 8 and 9 are in our units 64, which is like somewhere here. So at 64, basically, we don't have any orange. We don't have any contamination from the scramble search. It means that everything which is beyond 64 is basically clean, and whatever we detect with our detection completeness is okay, and we can use it. Whereas for Kepler, here it is problematic. So whatever we lost on the completeness, it is because we had to pay it for this reliability. And the question arises, who wins? Yes, we are reliable, but if we don't detect anything, there is no point on being reliable. So we should ask a question of, do we get any benefit from running all of this process? And the answer comes from an experiment like that. So we took the scramble tests, which are these not like solid lines, and we took the injection tests, which are the dashed lines. And basically we asked the following question: reliability in principle should set for us the detection threshold. What is the fraction of planets that cross this new detection threshold? So Kepler says, oh, threshold is 7.1 sigma, just because we think it should be 7.1 sigma. And then many things which crossed the threshold of 7.1 sigma were false alarms. We're saying no. We would first measure the false alarms, calculate where should the threshold be, and then ask who will cross the threshold. So if we use the regular detection statistic, not this non-Gaussianity corrected everything, we will get this blue distribution of noise events. And then in order to set the detection threshold, we need to like integrate the false alarm rate here. And when it reaches like something, we put a line of, okay, this is the detection threshold. So for example, like here, we decided to say, okay, let the background rate to be this 10 to the minus 6 times something, and then we put the detection threshold when it crosses the distribution. And for the same rate, the detection threshold for the new detection statistic, this one, the corrected one, it will be here. So thanks to the reliability correction, we shifted the detection threshold to be lower. And now we also lost the signal to noise of injections. And now, yeah, we got from here to here, and we're asking what is the fraction of injections which crossed for blue the blue threshold, or for orange the orange threshold. And it turns out to be that there is a parameter space in which it is enhanced. So there are more orange things which cross the orange threshold than blue things which cross the blue threshold. And it is shown here. So this is the detection fraction of injections that cross the threshold as function of this detection statistic. And if we use the regular statistic for detection, we get this. So we can only get detectable after like 75-ish. And if we use the new statistic, then we can detect part of the events also here. So we get this gap of events that previously we could not confidently claim their planets because of the contamination. And now we still are able to detect it, but now we can detect them reliably.
Can I ask a quick clarification? So I guess I'm a little bit confused about putting the two different multiple event statistics on the same figure if they're calculated in different ways. In other words, if I take given light curve, it will have a different MES calculated through your non-Gaussian approach and the Gaussian approach.
Yeah, so here it is indeed tricky to plot it. So for every event, I can calculate the normal detection statistic,
Right.
which I show to be very similar to the Kepler detection statistic. And for the same event, I can calculate this new IMES. And the question is, like, I can use this one as an indexing of, okay, which kind of signal I'm looking at. But for detection, I can use either this or the IMES. So like there is some label of the event, and there is a detection statistic which I actually use for detection. So here, this normal MES is used as a label, and the difference is which one I used for the detection.
Okay, but so on the previous figure, you were using the.
Yeah, on the previous figure, so for blue, it is the
Right,
regular
right,
statistic,
okay.
and for the orange, it is the new
Okay,
statistic.
so for example, the fact that if I compare the solid blue to the solid orange, that it moves to lower SNR, that seems like a good thing, like, oh, I can detect things at lower SNR, but it could also just be that the same event has a different value.
Yeah, exactly. So
Okay.
this is why what we look at is the comparison between which part of injections are to the right side of a given injection. Yeah, like you're completely right. We can just take everything and divide by 2, it will not change anything.
Right,
Yes,
okay.
exactly. Yes. Yeah, and finally, we run this detection pipeline on everything, and we got some catalog of detections. Almost all of them are in the Kepler threshold crossing event list or Kepler KOI list. So Kepler knows that there is something going on there, but they are not confirmed. They're candidates. Kepler does not know exactly whether they're planets or noise. And what we can do is for every one of them, we calculate this P planet, and we can tell exactly what is the probability that each one of them is planet or noise. And now, those red points are Kepler confirmed planets, the ones that everybody uses for population estimation. And in addition to them, we can now add all of those candidates with their probabilities to be real. So we will enhance the number of points which are available for the population estimation, and we will attach weights to all of those points so that if they're not real, we don't screw up the population analysis. But
Question.
yes.
So for the red points, are they confirmed by other methods? So that's how.
Yeah, Kepler confirmed planets are a tricky thing. So in the beginning, the policy was that you can only get a label of confirmed if there is a follow-up, for example, the radial velocity, and somebody wrote a paper and you measure its mass. But then people started to do some statistical confirmation, some other kind of confirmation. And basically now I think if you write a paper and you reference it to the NASA archive and they agree that it's confident enough, they write that it is confirmed. I just talked to Steve Bryson a couple of days ago, and he says it is a big problem of labeling planets, and yeah.
This came up at the Exopag.
Yes, right. Yes.
Conversation between Jesse and Steve, and it's worse than what you described. If the refereed paper says it is a confirmed planet, then the archive takes it as a confirmed planet. Because they have no ability to vet.
Yes, and then for example,
Give me great confidence.
they fully rely on the community, and then, for example, if you do machine learning and you want to use confirmed planets as a training set, be very careful because it might be that they're not.
What is the typical P planet for the red points?
Yeah, so I showed it over here. So this is basically 1 minus P planet, whatever. So their P planets are usually very large. Like for my pipeline, they're usually very large. And noise-wise, so this is the pipeline which compares them to the statistical noise. Statistical noise-wise, they are usually good P planet, but they can be also background eclipsing binaries or something like that. So we need to implement the second step of the pipeline and test them against binaries or some other scenarios, which is also hard. And basically the vetting pipeline that people usually use is very hard to operate on low signal to noise events because you don't have basically any information about its shape, its centroid or something. We will use Gaia here because if there are some binaries, maybe Gaia will see them and like try to make it as good as possible, but still like our current approach is just to calculate what is the probability for them to be planet and not eclipsing binary. So I cannot give you a guarantee that for sure it's not going to be a binary. I will just apply the same kind of idea of weighing as I did for this reliability. So eventually it will have a weight of reliability of not being a noise and the weight of reliability of not being a binary, and both of them will go here and downweigh something suspicious. But as you can see, these are all to do. I'm still like working on them, hopefully sometime soon, but stay tuned. For now, the conclusion of this talk is that we enhance this. We have a way to include it into the population inference, like mathematically, and it allows us to include marginal events from the catalog and efficiently like use more information and not be afraid that something is just a noise false alarm. With this, I thank you for your attention, and I'm here today and tomorrow. Come talk to me and ask questions, and also tell me about your science because I want to hear it.
So you started talking very briefly about Gaia at the end. And one of the problems we had 10 years ago doing these statistics is Kepler was all we had. And now we have some Gaia and more to come. So how much do you expect things like excess astrometric noise to be useful prior, particularly for the long period ones where it's going to have the most leverage? It may not detect an orbit, but it can detect that there's something there that doesn't look like a single star.
Yeah, so I took all of my candidates and I looked up for the excessive astrometric noise and RUE, and there are some things which like have either large RUE or large RUE neighbor or something like that. I still have to like estimate what does it actually tell, what is the probability that there is just at random some large RUE, or does it mean that it's actually a contaminant? I still have to work it out. Yeah, but in general, probably some events will be just resolved as a binary star. The problem is in the periodicity that I'm searching. So the periods of like roughly 1 year will have just borderline separation for Gaia to be able to detect something there. So it happens that Gaia is useful potentially, but maybe exactly the periods that we need, it will have its detection limit and it's going to be hard again. Yeah, so I'm not exactly sure whether it's going to solve all of our problems, but it will solve a part of our problems.
Yeah, really nice work. Thanks for coming to share. Lots of details I'm curious about following up with, but one thing in the plot, I guess you just showed it again recently of the 1 minus log 1 minus p and for all the EIF. So clearly most of the data points there have the negative numbers, meaning it's 99.99. But for the points at 0, I'm concerned that it seems like since that point at 325, that's low as the legend point, it seems like all 3 of the
this is not point, it is, this is
so ignoring that, all 3 of the long period points, it seems, are not planets.
This is because of our completeness. It is because of the next slide, which just says that for those long periods, we are unlikely to detect stuff because of the non-Gaussian correction. So basically, we cannot tell whether these are planets or not, because in our opinion, given our non-Gaussian noise, they could have appeared also from the non-Gaussian noise. But what people in Kepler did, like these candidates were very important for them, especially this one. This is Kepler 252b, the favorite planet of John Jenkins, and they have paper about it specifically. So they looked at it very carefully, ran some additional tests, checked manually many false positive hypotheses and everything. And as far as they're concerned, it should be a planet. Statistics-wise, there were several papers claiming it is significant, then recalculating it, it's saying, oh, it's actually not significant, then recalculating again and saying it's actually is significant. So like it's a contested one. For now, everybody's convinced that it should be real, but just pipeline-wise, at least I am not able to say that it is like statistically significant. Yeah, and the same with those two. Like I'm actually not sure. Here I cannot see this -2 line is like 99%, but maybe it's like I don't know 50% or something though. So like -1 here is going to be 90% and here is going to be 50%. So maybe like this is 50%, maybe like I don't know. There is some probability that it is a planet, but yeah, we are bad at detecting very long periods.
There's a question on phone.
Yeah, I guess so you say you're working on the population inference, but it seems like this might lead to, say, a steeper distribution of probability, planet probability of the orbital period, or perhaps just greater uncertainty of the model.
Yeah, the fact that we don't detect this will just not enable us to precisely measure it. And yeah, if we don't detect anything here, we will just able to put some upper limits or something. Because we have the characterization of completeness and reliability, we will actually understand which upper limits we put there. But yes, this is true. With the current understanding of the noise, we cannot reliably say anything about this. There is another work of a group from Berkeley, I think, which figured out a different way how to account for this non-Gaussianity, and they actually have a better completeness. I am not sure about their reliability. They claim it should be fine. I was afraid to do what they did. So basically what they did is to treat the non-Gaussian noise not per star, but like generally, and then claim that all the false alarms, or at least like the significant portion of the false alarms, should come from the so-called rolling band artifact. And then they can and this rolling band artifact, it should be a quasi-periodic. So they basically detect this artifact separately, correct non-Gaussian noise separately, and then correct for the local or effect from the size of the search in like analytically. So they assume that the distribution should be fine. Then we analytically correct for the Lukasor effect, and then we add this a correction for the rolling band artifacts, and then they like don't have to punish every transit. What I'm saying, I don't know anything. Noise can be anything. It can be everywhere because I looked at the data. Everything looks so bad. I'm just gonna blindly take everybody, and if they're bad, just punish them because I was not sure. I could not trust the data enough to make some assumptions and hope that it will work, because what if it doesn't work? If I don't detect planets, okay, I will put upper limits. But if I do detect something and it turned out that my model was wrong and it's not a planet, this I don't want. So I was like more conservative. Maybe I did lose a lot of planets because of that, but
So there's a question online from Victor. They're asking, did you run your checks on the most controversial Kepler detections? Can you see anything on their false alarms versus real rate?
Yeah, so like one of the most controversial things was like this one, and I already discussed it. In general, for Kepler, there are a lot of candidates which are blue points here. So many of those candidates, they have like large signal to noise, but Kepler is aware that there might be events of the same signal to noise, but which are false alarms. So this is actually like what we do here. We take all of our detections, which also turned out to be Kepler candidates, and we calculate for them whether they have a large probability of being real. And just to be clear, there is probably around the same amount of points which did not make it to this plot, because here we start from p-planet 0.5. So they, in our opinion, were not high probability of being real. So probably there is a lot of Kepler candidates which we just don't think that they're planets. Maybe it is because we have a bad completeness, but if, like, regardless of that, if it was just a false alarm, it dropped by definition. So somewhere over here, there are all of those other candidates, including the ones which are actually false.
Thank you. Let's thank our speaker again.
Thank you.
And we will have a special assembly tomorrow, also at the place room. It's talking about the grid disks.